We are going to talk about three concepts, and that's the most probable speed, the average speed, and the RMS speed. Now when we are talking about these, that means we are actually talking about the gas molecules which are, let's say, placed in an enclosure, and if you are basically considering n number of gas molecules, the chances are that under a certain temperature the speed of each of these gas molecules will be different. So looking into the first concept, let's say there are 10 gas molecules, and out of that, let's say this is 110, one other speed is 110, maybe other one is 120, one is 130, again let's say 110, and then we have got 140, and we've got 100, and so on. So you can see that 110 is actually the speed which is most common. So that is what is the concept of most probable speed is. So that means most probable speed for this system of gases would be 110. But in general, if you want to write down a relation for finding out the most probable speed, which will obviously depend on the temperature, right? We do know that if we increase the temperature, the gas will start to vibrate rigorously. At the same time, their motion will be enhanced. So we can say that this depends on the temperature. But how is the relation? How we are going to find out the relation? This is something which we are going to do in today's class. But for that, first thing is important, and that is nothing but the Maxwell-Boltzmann distribution. So the Maxwell-Boltzmann distribution, although the derivation takes a bit of time, we are not going to derive that right now, but Maxwell-Boltzmann distribution tells me that what will be the speed of molecule within a certain range. Okay, so let me just write down this speed of molecule, let's say, in the range, okay, in the range v and or v to v plus dv. So this dv is a very small change in velocity. This was the velocity, let's say, between 110 and 110 plus 1. So what will be the speed within this range? Okay, and this is something which is actually given by the Maxwell-Boltzmann distribution, and how many molecules would be there which will be actually having the speed in this particular range, we can actually find it out using this formula, 4 pi n. So this number of molecules, dn number of molecules, will be having a speed within this range. Okay, so if you write it down in general and if you write down the formula, obviously it's a bit long, but anyway, we need to remember this, remember this if you want to derive the three kinds of speed that we are actually going to talk about. So this is m by 2 kt whole thing to the power 3 by 2 into e to the power minus mv square by 2 kt into v square dv, and that's it. Okay, so this is the formula that we should actually remember. Let me mark this as 1, and I hope you get the terms here. It's all simple. We have got n, which is the total number of molecules. dn is a small number of molecule which is having a speed in the range v to v plus dv. M is the mass of each of these molecules, okay, and then k is the Boltzmann constant, T is the temperature, and that's it. Okay, and v is obviously the velocity. So this is the Maxwell-Boltzmann distribution law, and we are going to use this to derive the three velocities that we are actually going to talk about. Now if I say something is most probable, so we are basically talking about a probabilistic idea. So the probabilistic idea would be that if we are basically considering how many particles are having a velocity v, okay, how many particles are having a velocity v, we have to use the concept of probability. And what is the idea of probability? The probability talks about something like this: number of favorable cases, divided by total cases, right? This is something which we know, divided by total. So if you look into this, the total the number of favorable cases, that means the particles having the speed between the range v and v plus dv, let's say, would be nothing but dn, and divided by the total number of cases, that means the total particle, which is nothing but n. So you can see here that we can just divide dn by n, and if we divide this side also by n, this n gets cancelled. So what I am getting is this 4 pi m by 2 kt to the power 3 by 2 e to the power minus mv square by 2 kt into v square dv. Now this is the concept that we are actually using, okay, to find out the answer to the most probable speed. But we have also got a constant concept of maxima in mathematics. We can actually use that as well. And what does it say? It says that if we are considering a function and if we are differentiating it with respect to a variable x, for maxima we can actually equate it with 0 and solve for x. Okay, so that is the idea. So the question here is that the maximum number of particles that are actually having a speed, okay, which is most probable, okay, which is the speed which is common to most of the particles. So for this, what we are going to do is we are going to equate it with 0. So what I am going to do is this, differentiating and equating to 0, equating to 0. So we can differentiate this entire term, and you can see what you have here is these terms. Okay, these are the terms that we are basically going to have. Okay, so let's do it. So if I just want to find out what is the most probable velocity, I can just take dp dv, because v is the variable here, and equate it with 0. So if we do that, what we can do is d dv of this entire term. So if we differentiate this entire term, we can see that this is something which is constant, so I can just take it out. So that's 4 pi into m by 2 kt whole thing to the power 3 by 2. Okay, so that's it, we have it here. And then we have to differentiate this. Now it's basically a two function here, one is this, one is this. Okay, so you can see here, if I actually differentiate this, I don't get this dv term because I can take d of this, okay, and then dv can come at the denominator, okay, and then we can actually have the d of this term. So if we differentiate this term, we are actually going to have two terms here. Let's look here. This is first term, so let me take this first term, and the second term is here, so let me take the second term outside, and the first term I can differentiate it. So this can be written as e to the power minus mv square by 2 kt into ddt of this term, right? So that's how we differentiate it. So we can write it down as minus m by 2 kt, that's fine, doesn't have anything to do with the differentiation, but v square, when we differentiate it, we will be getting it to be 2v. So that's the first part of the differentiation. In the second part, I can take this term outside, so we can take it, write it down as e to the power minus mv square divided by 2 kt into v square. If we differentiate it, we are going to get 2v dv. So now we have got these terms and we are going to equate it with 0. So let's see what happens now. We can actually see, we can take a number of terms outside which are basically common. So this term, this side is 0, this is the common term, so we can divide it by this term and we will be getting this, rid of this term. So we don't have this term now. Here also we can take certain things common, like this 2 and this 2 will actually get cancelled. So what I am left out with is this is v square and this is v. So there is a v here also. So what we can do is we can take those terms outside, right? So let me just write this down. If we take this outside, we can write down e to the power minus mv square divided by 2 kt, that is something which is common, and then we can take out one v here, so we can take this v common, and inside we are left out with, here we are left out with v square, and we can write down minus m by kt, right? So I hope it's clear to you, because we have taken this one common and we have taken a v common. See, this is common and the v is common, okay, not this dv, sorry, I have written this mistake, there should not be a dv here. Okay, so this is common. So what we can do now is we can differentiate this. So we can take the second part now, plus, and in the second part, if I have taken this and this common, we have just left out with the term 2 is equal to 0. So again, you can just get rid of this. just get rid of this. So we are finally left out with 2 minus mv square divided by kt and equated with 0, right. So that means if I want to find out v, I can take v on one side, mv square by kt is equal to 2, or we can take v square is equal to 2 kt divided by n. So you need to remember this result. This is the most probable velocity. Let me write it down as Vp, and this is root over 2 kt divided by n. So let's box this, and this is something which you should remember. Okay. So this was the first part where we are actually finding out the mean most probable velocity. In the second part, what we are going to do is we are going to find out what is the mean speed or the average speed. So let's find out the second result, which is the average or mean speed. Remember, in all the three cases we are going to use the Maxwell-Boltzmann distribution. So we are going to find out what is the average speed or the mean speed. So by average, I hope we all know, we get it, that if we are actually having these speeds 110, 110, 120, 115 and so on, we can add them up, add each of these speed and divide it by the total number of particles. So that is 4, right. So this is what we are going to do. This is the formula that we are going to use to find out the average or the mean speed. So let me just write it down. This is V average, okay, and we are going to consider the speed of each of these particles. The first particle is, let's say the speed is V1, the second is V2 and so on, and I am going to have n number of particles and the speed is Vn, so I will divide it by n. Now you know from the concept of integration that if you are taking small velocities and adding them up, we can in a way consider it and take the integration. So we are going to go from the speed, we are considering the speed, okay, and the speed can be anything, it can be 0 or it can be to a very high value, let's say infinity. So assuming hypothetically that the speed varies from 0 to infinity, we can write it down v dn, okay. So I hope you get this, because if you are considering, let's say, a speed v and it is connected with n number of particles, okay, that's the idea behind frequency, okay. If there are, suppose for this particular example, we can consider 2 into 110 plus 1 into 120 plus 1 into 115. So how many particles? 2. So that's n, and that's a small number of particles. So let's take dn. What is the speed? V. So v into dn. So v into dn, this one will be nothing but again n into, so this is v1 into v2 and so on, okay. So if we keep on adding them up, what we can do is we can use this concept of integration and find out what is the total particle, okay, with this much velocity. So we will divide this divided by n. So this is for a gas which is having n number of molecules, okay. So this is the basic idea for this, okay. Now what we can do is we can again use the Maxwell-Boltzmann distribution and we can write down this as dn, okay, and dn is equal to 4 pi and n, okay. We are not going to repeat this, let me just write it down directly. We know what is dn, so let's just directly put it in the result, okay. Let's just directly put it in the result. So what we can do is I can going to find out the average speed. So v average is equal to, we are going to integrate it, so let me just divide it by n here, and then if we integrate it from 0 to infinity, v is there, so I will keep it v, and dn we are getting it from the Maxwell-Boltzmann distribution. We can write it down as 4 pi n into m by 2 kt whole thing to the power 3 by 2 into e to the power minus mv square by 2 kt into v square dv, right. So we have all the terms in place. We are just going to integrate this, so we can cancel this out, okay, and then we can just do it simply. So we can write it down equal to, we can take out whatever is not dependent on v. This is 4 pi into m divided by 2kt whole thing to the power 3 by 2, and then we can actually do our integration 0 to infinity. There is a v here, there is a v square here, so I can write it down as v cubed into e to the power, so we have just left out with e to the power minus m v square by 2 k t dv. Now in exams and all, you really don't need to do this integration because this is going to be very long. So the best idea would be to remember a certain standard result and actually use it. Okay, so we do have some, okay, sorry for that, we do have some standard results that we can actually use. Okay, and let me just write down one standard result for you in this particular case. Although if you keep practicing and you are doing a lot of numericals in quantum mechanics, statistical mechanics, you will see that these results are very common and we usually use it. Okay, they basically are used using gamma functions and all, they can be solved. So this is of the same form. See, v cubed e to the power minus mv square by 2 kt, it is e to the power minus bv, that means v is equal to m by 2 kt. You can compare it and write it down. So if you get a result like this, the standard answer to this is 1 divided by 2b square. You can always simplify this, okay, and try to practice it for your own confidence, but at this point of time when you are solving this is very long, so you really don't have time to solve it, so that's why you can write it directly. So I can write it down as 4 pi into m divided by 2 kt whole thing to the power 3 by 2, and this integration would be nothing but 1 divided by 2b square. Okay, but you have to be very careful about one thing, because there are standard integrals from minus infinity to plus infinity that will give you a different result altogether. It's 0 to infinity, so this is the standard result, so make sure that you don't mix up. Okay, but I won't write down b here, because I already know what is my b. In this particular case, m by 2 kt, that's my b, so I can write it down as m by 2 kt whole square. So m by 2 kt, this is also m by 2 kt, so we can kind of do some simplifications here, right? So let's do it. Okay, let's see what result we are getting. So cancel this, I'm going to get a 2 here. Okay, and then we can take this, so it is 2 pi into m by 2 kt whole thing to the power 3 by 2 minus 2. Okay, that's it. So if you take the LCM, this would be 2 pi and this is m by 2 kt. So LCM you take it 2, so it's 3 minus 4, so that's 2 minus 1 by 2, so it's minus half, minus of 1 by 2. Okay, so we can take that. Okay, 3 minus 4, okay, this is fine. So if we just simplify this, okay, this would be nothing but 2 pi into root over, there is a minus, so I can take it in the other way around, 2 kt divided by m. I hope you get this. Okay, it is 1 divided by m by 2 kt root over, so it will be 2 kt divided by m. Okay, so this is one answer that you can write it down in this form, or what you can do is you can take everything inside the bracket or inside the root, sorry. So the v average result would be like this. Okay, if you take this 2 inside, so that would become 4. Okay, so that would become 4, so we can write it down in that form as well. Okay, so I think we missed out on something here which was actually important on the Boltzmann formula. Sorry, there is one mistake here. There should be a pi here, please include a pi. There should be a pi here. There is a pi here. Okay, and then there is a pi at the denominator. Okay, that's why, okay, there is a mistake. So again there is a pi here. Okay, so that means what result we have is this. We can take it to the power minus by 2. There is a pi here, so if I just separate it out, we are left out with this pi. So it is 1 divided by pi to the power 3 by 2. So that is something which we missed. So let me write it down, 1 divided by pi to the power 3 by 2. That means I can write it down as pi to the power 3 by 2. So that result will definitely be there. 1 divided by pi to the power 3 by 2. This is 1 divided by pi to the power 3 by 2. Okay, so this result we should keep. So now if we actually simplify this, we can write it down as 2 into pi. There is a 1 for this, and this is minus 3 by 2, so I can take it to be minus 3 by 2 into root over 2 kt divided by m. So if this 2 can be taken inside, it will become 2 square, so that would be 4, and this is pi to the power 1 minus 3 by 2. So I can write it down one more line, 2 pi 3 by 2. So this is 2 minus 1. Okay, so that 3, that is minus half, so it is nothing but you are getting it to be minus half root over 2 kt by m. So now we actually have the final result. The final result would be V average. You can write it down in this form also, but then we can take it inside the root, everything inside the root. 2 goes inside the root, will become 4. 4 into 2 is 8, so I can write it down as 8 kt divided by m into pi. So that's my result. So this is the average speed. Okay, so that's there. The third thing that we actually want to do is called the RMS speed. So RMS is a term which you might have heard about before also. There is root mean square speed, root mean square velocity, and so on. Okay, we are going to talk about root mean square speed here, and if you remember root mean square current when we're talking about RMS current and so on. Okay, that is also there, the concept. But this definition is quite simple. This is VRMS square, and you have to just integrate this. Okay, integrate this. You will take the integration from 0 to infinity, and this time it is V square d n by divided by n. So if you check it with the previous result or previous integration, it's almost the same. So it's all the same, except the value v square. We are taking the root mean square, so we are going to take this square. Okay, so we have a square term here, so that means whatever result we are going to get is here. This is v square, and there is another v square, so this will become v to the power 4. So that means we have to use one more standard result, okay, here in this particular case. And maybe even if I don't derive it, you can actually derive it. It's very simple. If I just give you the result, it is 0 to infinity. I will give you the standard integral that you have to use, v to the power 4 e to the power minus mv square divided by 2 kt into dv. We need the standard integral for this. Okay, let's take this m by 2 kt as b. Okay, if we do that, we are going to get it to be 3 by 8. This is again something which is the standard result, into pi divided by b to the power 5. Okay, pi divided by b to the power 5. That's the standard result. And what is my b? B is equal to m divided by 2 kt. So what we have to do is we have to do the same integration here, whatever we have done in the last case, but only we have to use this standard integral. So that is important. Okay, so if we do that, okay, we can actually get our answer very easily. I'm not doing it because you can use this result, put it there, and you are going to get the same answer or similar answer. But when you simplify this, you are going to get it like this: VRMS square is equal to 3 kt divided by m. So that is what you are going to get. But we need VRMS, so that means my VRMS is equal to root 3 kt. Since I have given the last integration in detail, so I am expecting that you will be able to solve this integral, because the standard result I have already provided, and based on that you can understand that how you are getting it to be root over 3 kt divided by n. Now then what is the comparison between the two? Okay, between the three, the comparison is also important. So comparison, let's just check out the comparison. Okay, comparison between V most probable, V average, and V RMS. Let's take the ratio of all these three. Okay, and we already know the result, and I would suggest all of you to remember this result. Okay, these kind of questions are also being asked in the entrance exams, not the derivation part, rather the final result and its application. So root over 2 kT divided by m. For V average I am getting root over of 8 kT divided by pi m, and the third one would be root over of 3 kT divided by m. So we are getting three results here, and we can see that kT divided by m is something which is common. So if we just simplify it further, we can cancel out all the kT divided by m. So this would be resulting in root over of 2 ratio of root over of 8 by pi and root over of 3. We can remove this kT by m here, kT by m here, kT by m here, and we are getting this result. Now if you check the value, root over of 2 and root over of 3, obviously it's greater than root over of 2, and root over of 8 by pi will lie somewhere in the middle, because pi is 3.14. You divide it and you can check the calculation and the results, and based on this what we can say is that this mean speed that we are actually talking about is the least, always that's the least value, and the average would be somewhere in the middle. Okay, let me write it down as V mean, and the maximum value would be for RMS. So in this way we can actually compare the three results and definitely say that the root mean square speed of the gas molecules will be maximum, the most probable speed for the gas molecules would be minimum, and the average speed will be lying between these two values. Okay. So that's it for these three results. A very important result when we are using the Maxwell-Boltzmann distribution to find out what are the velocities involved when a gas molecule is under the influence of certain temperature.